So if we want to make confidence intervals to open up our options and a better chance of being accurate, we work in this case in terms of z-scores and that value p hat, where our margin of error here comes from the approximation of the binomial distribution with the normal. That is, E is equal to z sub c times the square root of p hat q hat over n. It's a kind of odd value, but if you did some of those last problems in the 5.4 homework, you saw a touch of it going on there, where we make our interval in the same way as before. We take that margin of error E and add it and subtract it from our point estimate. That is, we are aiming to get P inside of P hat minus E to P hat plus E, where in particular our required bit of information to make the central limit theorem, as it were, hold is that n p hat and n q hat are both larger than 5. But really, when we're looking at these things, they're going to be considerably larger than 5, so we won't have to worry about that too much. But let's take an example. So here, we want to use the previous example to construct a 95% confidence interval for the population proportion of US adults who use Facebook. So, in our previous example, we had that p hat was equal to 0.68, which means that as a result, q hat is equal to 0.32. And usually, np hat and nq hat are going to be perfectly fine for what we need. In this case, we're just going to see what that looks like to be sure, where n times p hat is going to be 1550 times 0.68, which ends up being 1054. Hopefully you can tell, at least a little bit bigger than 5. And similarly, n q hat is going to be that same 1550 times 0.32. Here we get 496, which is still considerably larger than 5. Generally, that's going to happen. It's going to be almost comical how much bigger our value is than the minimum we need in order for the central limit theorem to hold. But we still want to check. Anyway, we're fine on our most basic step for this kind of problem. Then we want to get the value E, where E follows that formula. Here, that would be z sub c, but since we want a specifically 95% confidence interval with a z-score that's one of those common ones that's going to come up a lot, that would be a z-score of 1.96 multiplied by the square root of p hat q hat over n, p hat q hat, and then I didn't write n, but let's just remind ourselves that n is 1550, as we saw in the previous example. So we have 0.68 times 0.32 over 1550. That lovely mess of things, we check out and get a value of 0.023. And once we have that, we're just going to take it and add it and subtract it from our value for p hat. So we're going to take p hat 0.68 minus 0.023, say that this is less than the proportion we're aiming for, p, and say that that p is less than 0.68 plus our margin of error, 0.023, where you pull those in, take those out as appropriate, and we get that our 95% confidence interval is going to be, oh, that's not a 0.68. I get 8s and 5s mixed up sometimes in my own typing, much less my own handwriting. But in here, we will go from 0.657 to 0.703. And I know what many of you are wondering right now. You did this by hand. Does that mean we have to do this by hand? The answer to your question is, of course, no. You don't, but it's important that you see this stuff by hand at least once. For these types of problems, we have another computation built into the calculator that handles these with greater efficiency than the work I just went through. We have the one proportion z interval computation, where you plug in those numbers, you run it, and you're going to get the value that you want, or more appropriately, the range of values that you want here, which say that with 95% confidence, the proportion of adults using Facebook in these United States is between 65.7% and 70.3%.
Now I see you're trying to use your style over mine.
And just for fun and thoroughness, we're going to get one more example here before looking at our last thing for the chapter.